Hello, and welcome back to Geo 572 Advanced Hydrogeology. So today we're going to refocus our attention on boundary conditions. And it's hard for me to overemphasize the importance of boundary conditions, understanding boundary conditions, and applying the correct boundary conditions. So boundary conditions are one of the most important things that we're going to do as part of conceptual model building and then numerical model implementation. So recall that what we are solving when we're modeling, we are solving the boundary value problem. So boundary value problem, and that's the BVP, and the name boundary says it all right? The boundaries control our solution, all right? They control the solution to our PDE. So the boundary value problem is a solution to a PDE, all right, given the boundaries. So recall, like, for example, we've been working with this PDE a lot. SS dH dt is equal to K d squared H dx squared, and I'm going to add a term here, plus R, where R is sources or sinks of water. In our domain, all right? Okay, so the boundary conditions are the key to solving this PDE for our situation, all right? And I want you to recall there's three main types of boundary conditions. So the first, Dirichlet. And in a Dirichlet, what we're doing is, recall that H here, H is our variable, all right? So in a Dirichlet, we prescribe the value of the variable, all right? So in this case, H. All right, so we would say here, as an example, H is equal to some function, and that function is here a function of, could be a function of space and time, all right? Actually, it's a function of the boundary and time. Okay, so that's Dirichlet. We specify H, the variable. All right, the second kind is a Neumann. All right, and in a Neumann, we prescribe the gradient of the variable. So here, dH dx, all right? We prescribe the gradient. So here, we say dH dx is some function. dH dx on the boundary is equal to some function of time. And that's really how I should write this one up here. I'm going to get rid of this guy. This is a more correct way. H on the boundary omega is equal to some function of time. Okay, We can either prescribe the variable, we can prescribe the gradient of the variable. For groundwater, we've got another little trick here. If we remember that Q is equal to K times dH dx, then prescribing the head gradient is equivalent to prescribing the flux, right? It's just related by K. These two are the same thing. If I prescribe the gradient and I know the hydraulic conductivity, I'm basically prescribing the flux. So in groundwater, we also often call this a prescribed flux. All right. And, but really, mathematically, it boils down to this second type, we're prescribing the gradient. All right, and then the third type is really kind of a class. The third type is called, I'm going to call mixed species, and that is where we have a mixture of flux and gradient. All right, so here you might say the flux is a function of the head gradient at the boundary. This head gradient has to take into account head within the boundary, near the boundary. Okay, so these are our three types. And what I want to do now is talk about how we implement them in MODFLOW. So let's make a little drawing here. So I'm going to start off with a land surface. Okay, and I'm going to add a mountain range in brown here. And this mountain range cruises up here. Okay. And let's see, in our land surface, let's extend this picture a little bit. I've got a little channel here, it goes out. And here is the bed of a really big lake. So I got a lake here. I've got a little channel here. And I'm going to add 3 layers. So 1 layer here, another thin layer here, another layer here, and then beneath that, another layer. And this upper one is sandy and an aquifer. This guy here is clayey, sand, another aquifer, clay. All right, so this is a cross-section view of a potential model. And let's see, what else do I want to do here? I'm going to add in a well that's pumping from this lower aquifer. This might be starting to look a little bit like a conceptual model we might have been talking about lately. All right, so this well is pumping here. And what else do we know? Well, rain falls on our surface. So we got that going for us. Okay, let's talk about some of the boundary conditions we might have here. Well, this is a big old lake. All right, and so we might say, well, this is a constant head boundary condition. Here is a little ditch. We'll talk about that a little later, but that's an important one. Right here, we're receiving rainfall on the top of our aquifer here. So let's call this a recharge condition. All right. Down here, we got an aquitard. So let's call this boundary no flow. So now I'm starting to sketch a little boundary here where I've got constant head. I've got no flow. I've got recharge. I've got this pumping. All right. And then over here, let's do this. So let's say, hey, we've got some water table in our aquifer here. All right, and it kind of heads up here, and then magic happens. And we don't know exactly what it does in the mountain, but I'm going to say that in the mountain it does something like this. So this is what it looks like in the mountain. Okay, and so one of the things we'll talk about here is what this boundary alongside here might look like. Okay, so this is a set of boundary conditions or boundaries that we might be trying to implement in MODFLOW. And so let's talk about how we would do that. So how would we implement this set of boundaries in MODFLOW? Well, the first thing I want you to remember is that for MODFLOW, everything that we prescribe, recharge or head or these other types of boundary conditions that I'm going to talk to you about, or pump rate, Q, all right? All of those are constant for a stress period. So MODFLOW, remember, all BCs and sources and sinks, constant for a stress period. That is, we define them for a stress period, and if we want them to change, then we've got to define multiple stress periods, all right? So we accomplish this F of T up here by breaking time up into a series of stress periods in MODFLOW. All right, so first of all, also, MODFLOW does everything in packages. So the first package we're going to consider is basic package. And basic package allows us to define basically two types of boundary conditions. One is the constant head. All right, and we do that via I-bound. All right, so anywhere I had a constant head, say along this gradient, I would use the basic package and I-bound to set a constant head here. All right, now the other one that we can do here is by essentially not specifying a boundary condition, but it's still, we don't have to invoke another package, no flow. If I don't assign a boundary condition in MODFLOW, then it will treat all these boundaries as a no flow. All right, and the no flow is just a special case of constant flux. But these are the two boundary conditions I can apply. All right, so no flow, this one is basic package. All right, and I can do both of those just with the I-bound. All right, so the next question is, well, how do I handle this recharge boundary? All right, so for all the rest, so all of the rest of the boundary conditions, we're going to need different packages, and they're lumped under what they call stress packages. All these other packages are lumped under this classifier of stress packages. All right. And the first one we're going to talk about would deal with our top boundary, and that is the recharge package. And the recharge package is basically a Neumann boundary condition. It's a specified or constant flux for a given. All right, it's constant flux. I'm going to say that because it is constant for a stress period. All right, now there's a caveat, but it's only for aerial recharge. It only applies because MODFLOW has gone about this thinking about it as groundwater scientists. It only applies for gradients or fluxes coming into the domain from the top of the domain. So it's aerial flux at the top of the domain. You can sort of trick it and tell it where the top of the domain is, but that's what it's designed for. So it's aerial only. So this we could use the recharge package here, and what we define is Q sub R, the aerial recharge flux. And this can be constant over the whole domain. We can change it spatially. We can define it for each cell at the top of the domain, but it is always constant for a stress period. All right, and we define the flux. All right, and so the unit of that is length per time. Sorry, let me clean this up. Unit is length per time. Okay, stress package or recharge package. Okay, that does this, guys. So this one is the recharge package. Now, the next thing I want to deal with is the discharge here. This is a source or a sink. So this would be R in our equation. A source or a sink, it's at what R tells me is the location and the volume, the volumetric discharge of flux out of here. And so we implement that in MODFLOW with the well package. And the well package is a volumetric source or sink. At a location. Okay, so it's important. I can either inject or I can extract water. All right. In general, we think of positive flux or positive injection as something going into the aquifer and negative as something coming out. So this here, we define Q sub P. All right. And that is the volumetric source. So this would be length cubed per time. All right. And this is the pump rate at a location or the injection rate. Pump or injection at a location. Okay. Well package. All right. So now I've handled this boundary, this boundary and this source sink. So here's a question: how would I handle this side? Well, one way to think about it is that this mountain is full of water. It's got a lot of water, and the head inside the mountain right here near the boundary, I'm going to call that H sub M. Actually, let me change its location really quick. The head inside the mountain right here, H sub M, is basically constant. All right, and it will transfer water into the model domain, H sub I. All right. If H sub I is lower than the mountain, then it will transfer, and it has to move it through bedrock right here. So we've got this K bedrock. All right, and so I could calculate if I, for example, at some time, if I knew H sub I could calculate the flux in here as Q is equal to K over L H sub I minus H sub M, right? Okay, so we can think about this as a conductance from the mountain and into the model domain. It depends upon the difference between the head and the mountain and in the model, and in the conductivity of the bedrock, which controls how fast water can move in and out, right? And this is called the general head package. And the general head basically says that the flux into or out of the domain is equal to this, I'm going to call it K hat, all right, times the difference of the head inside or outside our domain. So this is the head outside the domain. Here, I called it head mountain, minus the head inside the domain. So Hij, this is an active cell right next to the barrier, right? And K here is called the conductance. And it's basically equal to, say, the K of the bedrock over the sort of length of transport, or the distance between H sub M and H sub IJK. This is like a figment of our imagination. What we're going to assign is the conductance, all right? And so if this unit here is length over time, this unit is length, all right? Then our conductance should be 1 over time. And if we recall, hydraulic conductivity is length over time over length, we'd have 1 over time here. So the conductance should have a unit of 1 over time. So conductance, and the other thing we define here is H sub M, the head outside the boundary. All right, so this is a mixed type. So basically all the ones I'm going to talk about from this point on are mixed boundary conditions. All right, it is a flux that is dependent upon the gradient or the value of the head just inside the domain. And the other important thing about general head is if the head here is greater than the head in the mountain, we will drive flow out of the model. All right, so flux can be in or out. Depending on the head in the domain. All right, so critical water can go in or out of the model depending on how the head compares to the model. All right, I can have water moving either way. All right, so I've got this boundary, this boundary, this boundary. Now I've got a channel here, and there's a couple ways I can conceptualize this channel. So the first one we'll talk about is the river package. And the river package is basically an aerial adaptation of the general head package. And the idea behind the river package is that we've got our stream here. So here's our stream. And then there's some thin layer of hydraulic conductivity. And then beneath that is our model cell, H, I, J, K, all right? And so the flux into or out of the model will depend upon the head in the stream, H, river, all right? And then the conductance, I'm going to call that K river or K hat R. All right, so the flux, so in the river package, Q sub R is equal to K hat R, the conductance of the riverbed, times the river stage, H river. So K sub R is riverbed conductance. H sub R riv is river stage. And then, so this looks exactly like the general head. It's just that it allows us to define the geometry here of the stream independently of the geometry of our cells. So we're also going to define geometry of the stream. And then I don't want to get too far into this, but there's also a limit saying that if the head in the aquifer falls deep enough that there's a unsaturated zone between these two, then they become decoupled and you just lose at the maximum rate. So there's a maximum losing rate. Maximum losing rate. All right, so for all of these, you can get a way more detail on how we actually implement it in the MODFLOW manual. And I'm not going to give you the same details of the MODFLOW manual. I'm just here to give you the conceptual idea. And the basic idea is that you exchange depending upon the head. You can have water flow in to the river or out of the river. It can be a gaining or losing reach. Depends upon the difference in the water level between the stream and the groundwater. But if the groundwater level gets low enough, then you just are losing at some maximum rate. All right. Another way, another thing that we might have, let's just think about another process we might have. We may say that if the water level gets high enough, so let's say my water level rises and rises. So in spring, I got this higher water level and it intersects the land surface and I get a spring. All right, and I know that I've got springs at my mountain front, all right, when the water gets high enough. Well, the package we use for a setting like that is called the drain package. And the drain package is a one-way gate, all right? So the drain package is a one-way think about it as a one-way gate. And what it says is that the discharge, draining, all right, is equal to the conductance of the drain, say something to do with the spring orifice, how thin it is, times the head difference between the head in the model cell that has the drain and the head of the drain that we prescribe. All right, so that this might be the elevation of the spring, for example. All right, so here we supply K hat D and we supply HD, the head of the drain. All right. This only is true when HI J K is greater than HD. All right. If the head in our cell falls beneath HD, then we have no discharge. H. So QD goes to 0 when H is less than, when HI J is less than HD. All right, so if the head rises up high enough, we can flow water out of the spring, but when we drop the head, we're not receiving, there's no source of water there. All right, so that's the drain package. All right, the final package we're going to talk about tonight is the ET package. So in the ET package, we're simulating plants. All right, so here I've got a plant and it's sucking up water. All right, but remember that a plant has a root system. So if the water's basically up to the base of the plant's just using water as fast as it can. But if the water falls beneath the roots, right, then the plant can't use water anymore. So the ET package says there's some maximum rate at which the plant can draw water out, all right, that's ET max. And then there's some level, and that happens when the water's full, all right, or up as high as so that all the roots, the plant's using all the roots. If the water level drops to some level beneath the roots, then the ET goes to 0. So the ET package says that the flux from ET is equal to the maximum flux, ET max, when my head, I, J, K, near the domain is greater than some head that we define for ET max. All right, and this is basically the level at which all the roots are inundated and we have maxed out our ET rate. All right, then we say the ET discharge linearly varies between the ET max and 0 in this area where the head is between the maximum ET rate and this lower rate. So in this zone here, we're going to say ET varies linearly. As the head gets lower and lower, the plant can suck out less and less water. All right, and I want you to know that there's basically not a lot of physics behind this. It's just a way to sort of reasonably take care of this problem. Okay, so QET max times HI. I'm just going to go HI and leave out JK for simplicity. Minus the difference between HET max and HET none. All right, this is the head where you get no more ET. All right, over HET none. Okay, so as an example, when this guy goes to HET none, then I will have this product getting more and more negative, or sorry, smaller and smaller. And this is when the head H sub I is less than HET max and greater than HET none. Okay, finally, the ET flux goes to 0 when H is less than HET none. All right, so we've got this function that is a max when the head is high enough, it's 0 when the head is low enough, and it varies linearly between those two. So here we need to define QET max, HET max, and HET none. All right, and these are the three things we have to define. All right, so these are the boundary condition implementations we get in MODFLOW. We get an ET package, a drain package, a river package, a general head, and then recharge, constant flux, or constant head, I-bound. All right, and here you can see that we were able to do most of this, reasonably complicated and sort of standard groundwater flow problem with these packages. So river package, spring, we used the drain packet. We could use the drain package. And this guy would be the river package. And here we have the ET package. All right. Now, one of the things you're going to find as you go on in modeling is that not all of these implementations will cover all of the kind of boundary conditions that you conceptualize. One example might be that maybe we have a constant flux of water coming in from the mountain, and we want to assign a constant flux, but it's not aerial. It's along the side. All right, MODFLOW doesn't give us that option. So we've got to figure out a way to use one of these other options to mimic that. And one way we could do that is, for example, through the general head package, we could set the head really high, all right, 10,000 million feet. And the conductance to such a level that doesn't matter what this H here is doing, the difference between H sub ijk and H sub m is always basically the same as H sub m. And so H sub m really big times some conductance really small would give us the right flux. and it would be insensitive to what was happening inside the model domain. So those creative ways that we trick models into doing what we want them to do are something you're going to encounter with whatever model that you use. Okay, well, that's enough for tonight. I hope you guys have a good night, and I will see you in class tomorrow. Talk to you later. Bye.